Now we can start to record. Okay, guys. I hope you're okay. It's me again. And today I found my old electronic slides, so I'm going to do electronics with you guys. Share this slide. Okay. So many years ago, I taught a class on electronics, and luckily I saved the slides. This is from 2006, I think, 2007 maybe. That's how old these slides are. But the basics are the same. Electronics, you'll see the first 3 years of your classes basically are mostly the same as the classes that we took in the 1990s. It's the basics don't change. So you start out with this stuff. Oh dear. Okay, I'm gonna have to call them later. Okay, so amplifiers. So we start out with amplifiers. And so this is all about electronics. Okay, so most of you will take at least one class in electronics. I think you take 2 classes. I think mechatronics also takes 2 classes in electronics. And I'm just going to give you a feel for just the introduction, maybe the first class for this. Okay, so this is amplifiers. Let me make this a big. You see, I have an actual presentation. Okay, now I can't see you though. Okay, I think I got you guys back over here. All right, so amplifiers. So this is the idea behind an amplifier. The idea is, so this graph you're seeing, the x-axis is the input voltage to your system. So just imagine a system where you got this box, okay, and there's an input voltage and an output voltage. So something goes in, something goes out, right? But what is that voltage? So this is what this shows you. If the input voltage here is this voltage here, okay, V1. I really want to draw on this thing. This is why I quit having slides, because I can't really show anything on the slides. I'll put this in. Okay. And now I don't have my system set up. Okay. Just quickly. Okay, so this one's the one. Oh no. Another one. Sometimes if I touch it with the wrong mouse, it just stops working anyway. Yeah, this works. Okay, so what we're looking at here, this is the output voltage and this is the input voltage. So if the input voltage is this thing over here, let's call this voltage V1, then your output voltage is going to be, I don't know, V1 prime. Okay, so that's what the amplifier does. Like, imagine the amplifier is this box, and the input voltage is here, and this is your output voltage across the terminals over here. Okay, you'll often be drawing these graphs where you have input along the x-axis, output along the y-axis, because that's an easy way to see what the output is. When the input voltage is V2, you want to see an output voltage of V2 prime. Okay, so you basically look it up on this line. If the input voltage was this one, the output voltage would be this one. Okay, but you can see there's always like some kind of ceiling to this, because if you get as far as this voltage, okay, then it doesn't amplify anymore. So there's like a maximum voltage that you can have for the amplifier. And in fact, this is called clipping. Anything above V2, you get the same output V2 prime. It just can't, it just can't produce any more output. Why? Because it runs on power, it runs on batteries, right? There's a certain maximum power output that the system can have. And then, well, actually, it's about the semiconductor in it as well, but it's the physical limitations that mean that you can't get more than V2 prime. Now, sometimes what they do is they'll draw the input to the system, this V input, along here. So for this graph that you're seeing right here, this is this y-axis this way becomes time. Okay, so an input, you gave as input voltage to the system a cosine. Okay, which often happens if you have a communication system, you have a cosine. A lot of signals are cosine-like, similar to cosine, periodic. So yeah, you can have cosine-like signals a lot, and there's some signals, many signals, you can approximate using the sum of cosines. You'll see the Fourier series. Now you're in first, yeah, this is your first year, so you haven't seen these yet. You'll see the Fourier series analysis and the Fourier analysis of systems, and you'll see that any like periodic waveform, like square waves, if you had a square pulse wave, you can write that as the sum of cosines. Okay, so once we know how the system reacts to a cosine, we can calculate how it'll react to a square wave or to a triangle wave or to any other shape of periodic wave. So anyway, so that's why we're kind of interested in cosines. Now here we have as input to the system cosine. So at first we give it an input voltage of 0. And you can see at that point the output voltage is also 0. I'm going to draw the output voltage over here. And then the input voltage increases slightly. Okay, and then if you map this using this point, I'm going to map it not over here, but over here. And I'm going to make it like t time instance later here, right? You get this voltage at the output. If you give this voltage at the input, what do you get? You get this voltage at the output. Okay, so you can kind of draw the output voltage when the input voltage looks like this. Okay, so this is the input-output graph. You'll be drawing this for amplifiers, for instance, for op-amps and for like transistor amplifiers, stuff like that. It's just an easy way to see. Now, this is ideal because this goes like a straight line, perfectly linearly from the bottom to the top. It's pretty much ideal, other than the clipping. Oh, the clipping, let me explain the clipping. So if your input voltage went up too high, what happens? During this time period, it goes above the maximum input that we were allowing to the system. And then the output just becomes flat across that top. So you'll see this cosine going up, and then it's flat and then going down. Actually, sometimes we do this on purpose. This is a way to get a square wave from a cosine. You start out with a cosine wave, and then you clip the top, really low down. You can see, look, it looks like a square pulse wave. This is actually how my experiment, the communications lab systems work. They do clipping. So there's a cosine output, and you can see that because there's a little knob here, and there's a cosine output, and then it connects, and then there's a square wave output right there. So this is what they're doing between the cosine and the square wave. They're just clipping off the tops of the cosine, and they get a square wave. Okay, so this is the input-output graph. Now, this is, like I said, idealized. That's not the real thing because, okay, so linear signal application. Input times A gives output, okay? And the A is the amplifier gain, which is the slope of this line, right? Distortion changes waveform. This is a distortion. It's the clipping thing that's happening. And the thing is, like, even this is too good. We don't have any amplifiers that work like this. So amplification is a major thing, right? If you have a TV signal, you can't hear it, you amplify it. If you have a communication signal, when is the exam day, 14 or 21? I just looked at the notes. I don't know. I'll look it up towards the end of class, okay? The exam date. Just remind me again, Hamza, at the end of class. Okay, so going back to the amplifier. So this is still, in fact, in real life, this is the input-output curve for a transistor, okay? So it doesn't start linearly at 0 at all. In fact, it won't even start working until your input voltage is up to a certain level, okay? Your threshold voltage, because that you have to bias the amplifier. Okay, we'll get into that. So your input has to be above a certain level for this to work. Otherwise, look here, if the input is 1, the output is L minus. If the input is 2, the output is L minus. You can see like this clipped at the bottom as well. So what you do with transistors is called biasing the transistor. Okay, so the idea here is that you initially at the input, you show it a voltage which is above that. So let me put this here. Okay, so initially you make sure that you're applying this voltage VI. Okay, so this is what does the transistor look like? It says Pnp transistor here. I don't even remember this stuff, seriously. I don't do electronics, but anyway, you'll have these connected to ground. These are actually connected to each other, but sometimes it'll just like show this at the bottom of both of them. And then you assume. So this is like the sign for grounding. It's like this. This is a resistor. Okay, this one. And this is the shape that we use to show a transistor. And this one is usually connected to, you just throw a little button there and call that VCC. Okay, so this is, actually here it would be VEE, since I have drawn a common collector, I think is what I've drawn here. And then you have a resistance here as well, because you never want to connect any end of the transistor directly to your source, if at all possible. The reason is that you don't know anything about the source. I just draw VE here, and I assume, what do I assume is here? I assume here that there's a battery. Okay, so it's going to be a positive voltage. So it's going to go like this. I assume that there's this nice battery, and it provides me exactly the right amount of voltage here. But I can't guarantee that. That has an internal resistance and leakage, whatever. Like, it's got nonlinearity. So I put a little resistor here, which is higher than the internal resistance of this, whatever VE is, so that my calculations will come out according to my resistor rather than the resistor of the system, right? So usually you have resistors. And the general idea is initially to this base, you're going to the input, whatever, the input here is this one. Here, you're going to apply a direct current of VI. And the reason is to get the input right up here to begin with. Okay, and then, so you have like a battery that's applying VI over here. And then on top of that, you apply a little signal, your VI. We represent this using a small letter I. So this capital letter I is the voltage that gets your input all the way here. And then, but then you don't just apply this voltage, you wiggle it. Okay, so you basically, here you're applying this sawtooth wave, and it's adding to the big VI. So your input is going between this level and this level. So now when I map the output, you can see the output's going to be mapped to this voltage. Okay, so it's got amplitude bigger than the input voltage. We can't go too high. We'll go into this area. This is called the saturation region. If you go down here, this is called cutoff region. Okay, so you want to work in the amplifier region, which is kind of in here, right? And preferably in the linear part, because you can see as it's going towards the ends of the amplifier region, it's turning, it's twisting like this. It's not straight. Like, I wanted my amplifier to be nice and straight like it is over here, right? And that's not actually happening. So to make sure that it's almost straight, it's approximately straight, what I do is make sure this V input is it's smaller than this linear region. Okay, so this is how this is called a bipolar junction transistor. These are the transistors you often buy, and then there's FET transistors. This is the stuff that you will buy from electronic stores if you want to make like a hobby kit thing, like this FET transistors and BJT. These are called BJT transistors. BJTs and FETs are what you buy. But if you look at modern electronics, nothing. You'll just see a little chip, right? Well, inside that chip, there are CMOS transistors and MOS transistors generally. So yeah, they're still transistors. Really, the same basic principle exists. It's just they're tiny, and we don't usually buy any like if you're making a professional product, you're very unlikely to buy transistors unless you're doing power electronics. If you're looking at very high-powered systems, sometimes you're still using actual discrete components because they have to be big and they have a lot of heat to dissipate. So electronics doesn't work well with heat. So that's why, I mean, this stuff is the stuff you buy if you go to a store, you want to do like a hobby AM radio kit. You can buy these and put them together. You'll get a bunch of transistors and FET transistors in there. And we also use them in our labs to see how they work, right, at the most basic level. But this is what's done in the electronic circuits as well. You do biasing, Okay, so you learn how to do biasing of these amplifiers, and then you learn how to, and then you figure out, like, if I bias it exactly like this, what is this slope here? Like, when does it go into cutoff? When does it go into saturation? All of these voltages. And you figure these out, learn how to calculate these in your electronics classes. We often have to filter things. So this is a low-pass filter. Yeah, I've got a lot of concepts here. Okay, first of all, this thing. This is called a Bode plot because Mr. Bode came up with it. So here I showed you the response of the system to one particular sinusoid, right? And there's an amplification. Now this slope A that I have here, remember V input is A times V output. V output is A times V input. Well, it turns out that the response here actually also depends on your frequency, of the frequency of your of oscillation of the system. And you can design your system in such a way, actually, let me correct that, that's not true. For the transistor, for a single transistor, this is constant. But you can put multiple transistors together in such a way that some of them go into cutoff, or some of them go into saturation, or something at some frequency, right? So some of them don't work properly at a certain frequency. And this, using these properties, you design what are called filters. So basically, at least in communication in many areas, there's two major things you make with electronics. You make filters and you make amplifiers, okay? So amplifiers, we often show them like this, A, okay? And at the input, you'll apply a voltage, so it's the amplifier. At the input, we're going to do op amps next, and those are a little bit different, but these are regular amplifiers. You apply the input here, and you get the output here, and the output is equal to A times the input. Very important. You have a small input to your system, a small tiny voltage coming from your sensor. You need a larger voltage so you can measure it properly using your A to D converter and get it into your system. So you're going to need an amplifier, right? The TV doesn't pick up a signal, you amplify it so that it can recognize that signal. It can catch on to that signal. One thing about amplifiers is they amplify the signal, they will also amplify the noise. So remember we talked last week of signal to noise ratio. Signal to noise ratio was the power of the input signal divided by the power of the noise that's affecting your system, right? So the bad thing. Now the amplifier can't tell the difference between your signal and your noise. So most generally it will be amplifying your signal and your noise together. But sometimes you need to do that because your system can't recognize there's a signal if the signal has this tiny amplitude, right? You can't even lock onto this. It thinks this is 0. So what you need to do is make it bigger. So even if it's noisy, you can tell there's something there if you make it bigger, right? So amplification can be important. The other major component we use is filters. Now, the good thing about filters is they will pass, so it's like low-pass filters. They will pass certain frequency signals and stuff. Gosh, you guys have to take a little bit more electronics for me to talk about this. But basically, let me put it this way. Your signal might be changing like this. Okay, suppose this is your signal. It's just a cosine. When you add noise to it, maybe it looks like this. So you can overall see the shape, but there's this little buzzing going on top, right? And that little signal is changing very quickly. This happens a lot. The random motion produces a lot of these little changes in the signal, right? So this is your signal, and this is signal plus noise. A low-pass filter is a system that can't react very quickly to this buzzing. So it can't, the output can't go up as quickly as this signal does, and this tiny signal does, and go down. But it can go up slowly enough to follow the main signal, okay? So the output of the low-pass filter might be a little bit distorted, but see, it can't do that fast distortion. That's what I drew right now. It might be a little bit distorted, but it won't be like buzzy or fuzzy like this signal plus noise. So this is the output of low pass filter. In fact, if all of your noise is like changing really quickly like this, then you could eliminate all of that noise. You just make the circuit react more slowly than the noise does, and then all it sees is the average of the noise rather than it doesn't eliminate it. It sort of averages the noise, and if the noise is like up down up down up down, the average is going to be 0, right? So that's what a low pass filter does. It will pass slowly varying signals, low frequency signals, and it will stop the quickly varying signals, which are the high frequency signals. Now, it's not perfect. This one I show is not perfect because it'll pass the low frequency signal. So on the x-axis here, we see frequency. On the y-axis here, we see how much amplification happens for that frequency. Okay, so the A, think of this as A. So here it's showing that for low frequencies, so things that are varying slowly, then you have constant A, right? But as your frequency goes up, your A is decreasing. It's not amplifying. I'm not going to get into, I think we talked about decibels last week. This has decibels, and the x-axis will have a logarithmic scale. And when you do that, when the y-axis in decibels and the x-axis is logarithmic, this is called the Bode plot. I'll just write down Bode plot. So you've heard it. Bode plot. Shown on slides. In fact, let me copy paste it in so that you guys don't, you think this top part is the Bode plot. Let me copy that in so somebody doesn't, I'll do that later. Copy. I paste this here. Paste, yeah, there we go. This thing is called the Bode plot. Because Bode came up with it basically, but the idea is kind of like you have the logarithmic and then you have magnitude, and it has certain nice properties that you'll see that this kind of turns into a straight line for a first degree circuit, blah blah. We're not going to get into that. Phase response is separate from there. Let's not get into that either. That's all. Magnitude response, high pass. So high pass does the opposite, because sometimes it's the other way around. What can happen? I'll give you an example of this. If you have a signal that you're trying to transmit across, you know how they have those communication systems for power. So like you plug in one end to any mains outlet in your house, any electricity outlet in your house, and then you plug in another unit to another outlet, and it will transmit the signal across that area. Well, if you actually looked at the signal at the receiver, the raw signal at the receiver, then it would look like the sum of the 60 hertz signal plus your communication signal. And talk about high pass, the high pass signal. So suppose you're trying to send like a square wave. You have the 60 hertz power signal going across the wires, right? And then your signal is kind of added to that. So it's like hopefully not that much. And yes, it will cause problems for your electric. I don't think it causes problems for your electric devices. I'm going to guess this is not like a very high voltage signal. But I've always wondered if it's even possible to use it in Turkey, because we really have really bad quality of power. We tend to have just a lot of variations of fluctuations in voltage that cause devices to break down. So if you just try to communicate across it, there's already things like going up and down. And then you have this communication signal. You're trying to send it on 60 hertz. Now, at the receiver, you don't want the 60 hertz signal. You want your square waves, right? So now I don't want the slowly varying signal. I only want the quickly varying signal. Okay, so now I need a high pass filter. I need a high pass filter. And what that high pass filter will do is pass the quickly varying signal, stop the slowly varying signal. So the output, so this is signal plus 60 hertz power wave. So 50 hertz or 60 hertz power. And then at the output of this thing, I will see my nice square wave. Because 60 hertz variation is very small for the system. So that's called a high-pass filter. Okay, because it eliminates it passes high frequencies and eliminates low frequencies. Okay, so that one looks like this. Again, this is a first degree or just very basic high-pass filter. It passes the high frequencies, but then for the lower ones, the gain is going down as you decrease your frequency. Oh, by the way, there's no zero here, right? X-axis is logarithmic, and it will get to zero at negative infinity. Okay, so you can design a filter even using a single transistor, like I showed you. But here's the thing, you can buy an op-amp. The LM101 is a very popular op-amp that's been around forever. They use it for lots of applications, like any electronic kit that you get. It might have an LM101 in it, or a different type of op-amp. Op-amps are actually huge circuits. Actually, let me show you the inside of an op-amp. I had one in my other set of slides, I think. Lecture 2A. I don't know what this was or where I presented it, but okay. No, not here. Oh. Okay, never mind. Not here. Maybe in lecture 2. Okay, yeah. The top of this, yeah. This is the inside of that op-amp. Like, actually, the inside of this op-amp looks like this. There's actually 4 different op-amps inside one packet. Okay, and these are the inputs to the system, and this is the output, and the output is A times the input. Let's just say so. This is a plain old amplifier. Amplifies the difference between leg 12 and leg 13. So it's not; these are not directly connected to ground. Might be any signal you want to find the difference between. It could just be like you could connect 13 to ground and then have a signal on 12, right? But you can do other fun things with op-amps. Now the inside of one of these amplifiers looks like that other figure. Looks like this. So you can see there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 transistors. This is from the 741 op-amp, which is very, very popular. It has been since the 70s, basically. But each op-amp will have, newer op-amps, better op-amps will have even more transistors inside them. So in your electronics classes, initially, you'll learn how to analyze one transistor circuit. And then you'll talk about like 2 of these connected together. Like I think this was an input current mirror, for instance. And each of these like bits of the circuit actually have different roles. Like the role of this part is to make sure that you have a very high input impedance. So it won't draw any current in here. And then you also have this matching between the 2 to get rid of any biasing current. And then this upper part is to protect the voltage that you're applying from the power. And then, this part does the actual amplification. So each of these actually stages has a different role in your design. Anyway, so but you don't need to know any of that when you buy an op-amp. When you buy an op-amp, you just have this thing, and then you can put it in your circuit, and it works. So how does it work? The idea is, okay, so there's a common mode and a differential mode operation. In the common mode operation, you just apply a voltage to both of these, and then this is the inverting closed loop application. So you see at the output, you see, I think, the same voltage with a buffer. I don't remember what that did, but generally, the idea of the op-amp is the following. You apply a voltage to this one, V1, and then you could apply another voltage to V2, and this will not pick up any current. The current that comes in here is almost zero. The way it's designed is to make sure that this op-amp, kind of theoretically here, you can't see it, there's a blue triangle like this. But the op-amp should not take any energy, or just minimal amount of energy from V1 and V2. At the output, it will generate A times V2 minus V1. Okay? You almost always connect this feedback loop. This is this resistor back in. Because the current, most of the current going over this R1 also goes over R2. The goal of this part is actually feedback inside the to the op-amp, and it makes the op-amp more stable. If you just applied it without this top loop, you get much higher gain, but the gain changes a lot based on temperature and other constants. You really and the voltage and everything. So really you need R2 to make the system stable. Okay, so like I said, the idea here is the current goes in and none of it goes into the op-amp, really. All of it goes over here. And what you'll find is the output current is R2 divided by R1 times V1, and negative, just flipped over. So when this is 1, this is -1. So it works as an amplifier. Just a very, very easy way to implement the amplifier. You just see this plus and minus are the legs over here of the op-amp, the plus leg and the minus leg. And you put a resistor here and a resistor here, and you have an amplifier. You don't need to do any calculations. In electronics class, you'll learn things which are much more difficult. Okay, so anyway, there's a lot of things you can talk about this, and you will see all of these in your classes as time goes by, your electronics classes, and then you'll see, okay, ideally there's no current going here, but in reality there's a little bit of a current going in, and you know, all these different models. And you can make a buffer. One thing you should be aware of with any electronic circuit, we'll start with op-amps, is so far I showed an amplifier as a simple input-output system. I said if your input is this many volts, okay, your output is this many volts. Like it's just input to output. But the system takes a little while to change, okay, to adapt. And that you can't show on this figure. There's no time on this figure. I mean, there is time on this figure, but the input-output curve is not set to show time. In reality, it takes a little while for this circuit to adjust, for the voltages to change on the capacitors. It depends on the resistors that you tie as well. Large resistances generally means slowly adapting circuit. So this is showing a case where the input was changing too fast, and the output is supposed to be this black line. But the system never quite reaches it. It's trying to get down, but as this voltage is decreasing, the black line is decreasing even more. So much so that this black theoretical output, the output is supposed to be going up again. And that's the point at which this blue line catches the output, right? And then it starts going up again, but too slowly. Again, the circuit's just not adapting fast enough. And then the input is just changing too quickly. Okay, so instead of seeing this at the output, the black line at the output, what you see is these blue lines, right? This is slew rate limited. This is called slew rate. So the idea here is like this is a frequency. I can't adapt to whatever frequency this black thing is. It's too far above this, my frequency, adaptation frequency. This is not exactly low-pass filtering, although it has a component of it, because there are sudden changes in the output signal that mean high-frequency components. So anyway, what this means is that for any circuit you design, yes, you look at the input output and you do the biasing and you do the analysis, but you also have to see if the circuit can, in real time, adapt to the input that I'm giving it. So when you do, for instance, you'll be doing SPICE simulations of circuits. There'll be two different simulations that you do. One is for steady state. That's basically what we showed with the input output, the amplifier, right? When the input is this voltage, the output should be this voltage. You know, I'm applying this cosine. I should see at the output this other cosine, and kind of steady state analysis. But another analysis is the transient analysis. And the reason you do a transient analysis is stuff like this. Can I see how quickly this system is adapting, how quickly those capacitors are loading up with charge, and you know what the exact output looks like in the time domain, because it may be different from what you're expecting. Yeah, again, semiconductors, cathode, anode. So this is what a diode looks like in, okay, diodes. Let's talk about diodes. This symbol is the symbol. So I was showing you the symbol kind of for a transistor, right? A transistor, there's two symbols actually. There's the transistor, BJT transistor. I generally we put on the other side, don't we? This, like this, kind of. Okay, so this is the base. This is the cathode C. I forgot what the C stood for. I'll look it up. And E is the emitter, okay, for a BJT transistor. And you'll also have this arrow going in the opposite direction. The arrow actually points from the P to the N. So this is actually a PNP. The N is the base, and the C and the E are P's, and I know because the P is pointing to the N. And then you can also have it this way, okay? So this is still the emitter, this is still the collector, and this one's still the base. This is an NPN transistor, okay? So this is BJT transistors. And then you have FET transistors, and from what I recall, they look almost the same. It's a JFET, junction field effect transistor. And it too has a basic collector and emitter and the same kind of deal. There's also Mosfet transistors. See, that goes into VLSI. I never took VLSI. So I think they have like 2 lines on top. I'll look it up. I'll look it up and put a proper diagram for them, for that as well. And you guys can look it up as well. Look up what Mosfet transistors look like. The other thing we work with in semiconductors is diodes. Those are simpler. The symbol for a diode is kind of like a one-way sign. So most generally, we'll say with diodes is the current will go in this direction, but never in the opposite direction. So if your current is going this way, it's great. The diode is just remove the diode and put a straight line there. It's just a wire. But if the current starts to go in this opposite direction, it can't. It's like a one-way street. The current can't go in this direction, so therefore it's like an open circuit. So when you look at, we don't look up V input, V output. We generally look at voltage versus current graphs for this. So as long as your voltage is negative, nothing happens. Your current is 0. But if your voltage starts to become positive, it can't, because no positive voltage can ever accumulate across the wire. Just the current just goes straight across, goes forward. Okay, so that's what a diode does. Actually, let me jump to why this happens. What are semiconductors, really? Semiconductors are made from like silicon with an extra element in it. You kind of put an impurity in there. Okay, normally the way silicon is connected at room temperature is through covalent bonds, right? So if you remember, if you take into chemistry, you've seen covalent bonds. Covalent bonds are very strong bonds that form when two elements, no, what's it called? Elements? Atoms? No, atoms. Yeah, anyway, they're sharing an electron. I guess they're atoms, yeah. They're atoms and they're sharing an electron, right? One or more electrons. And the way silicon works is it basically gets into this formation where it has bonds with all the atoms above it and next to it, like carbon with graphene. And it has a very stable structure like this. And it doesn't conduct anything when it's like this. However, what they do is to put extra elements of different types in it, right? These are the impurities that they inject in there. And this element is looking for, what was it that they put? I forget which element it was, but this one actually wants 5 electrons. So it has this whole situation where it has an extra electron going around, and it can't form a bond with any of the other 4 carbons next to it. And the way the crystalline structure is, it's kind of forced to sit there with an extra electron, but it's always looking to throw the extra electron, try and make a covalent bond. And then they have another impurity. This is the N-type semiconductor, and this is the P-type semiconductor. This one has an impurity that wants 3 covalent bonds. So it's always like missing one of the bonds in there, right? So this carbon is always looking for an extra electron to connect to, and there's no electron over here. So what happens is at the slightest positive voltage, right, the extra electrons on this side, the minus side has the extra electrons, just go for the plus side, right, and try to fill in those holes, because this guy has an extra electron and this one needs an extra electron. So at the slightest voltage, they will just change places and send the electron along, right, into where it actually belongs. If there was a carbon there, that's where it would be, right? And that's kind of this voltage over here. As soon as you increase this potential above this, what happens is it kind of becomes, there's that electron that's running around, like it is in a wire, right, where there's a metal and there's no covalent bonds, and all the electrons in normal metals, all the electrons are running around, right? But here, there's only that one electron that's extra over here, and it can hop to this one. This is called a hole. You see, it has this hole over here. So this kind of position where there's no electron is called a hole. So the electrons just jump into the holes and go along, right? Okay, so this is a diffusion current, and drift current goes in this way, and this diffusion current, blah, blah. Anyway, so that's kind of the chemical basis of how this thing is a diode, essentially. So it conducts in one direction, doesn't conduct in the other direction. Actually, there's a barrier voltage in the other direction. It doesn't, the electrons don't want to travel back this way because they're already extra in this way. They want to go in this direction, which means the actual current goes in, I guess, this direction. So I've kind of reached the end of what I remember. So anyway, yeah, so that's the way kind of the PN junction works. You introduce this extra elements, a plus on one side, a minus on the other side, and then you have the electron that could move along if you give it a little bit extra energy, so it can jump out of these covalent bonds and move along. And it's not stable in a covalent bond. You couldn't break up a regular covalent bond using just the energy that you apply, the voltage you apply. Okay, now in reality, again, you need a tiny positive voltage for the electrons to kind of break free and move along, right? So if you apply a tiny positive voltage, this is like 0.7 volts over here. Okay, usually it's between 0.5, 0.7 volts, depending on the particular type of semiconductor you're using. Once you apply that 4-volt voltage, you'll get infinite current. Okay. And there's actually another area that you know, those electrons don't want to move in the opposite direction, but if you apply enough voltage, eventually it will conduct in the opposite direction. For most diodes, this is a breakdown point and something you don't want. It will actually, it could damage the diode. It'll get too hot. But there's a special type of diode called the Zener diode, which you use mainly in this breakdown. See, that's called the Zener voltage, by the way. So those diodes are used reverse. In the reverse direction, they can actually handle more current, but they have to be specially built for that. So it's forward voltage, backward voltage. So I guess what I want you to take away from this is that in electronics, most of the time, what you're going to do is to try to achieve some kind of ideal function. So for a diode, this is a function where current will go in one direction. I'll tell you at the end. Well, current will go in one direction and won't go in the opposite direction. Okay, so that's an ideal. Or for an amplifier, your input voltage is multiplied by A, right? And that's the output. So these are the ideal things that we want. But in reality, we have to deal with physical things, which are made up of these bonds, right? The stuff you learn about in chemistry. And using these, we have to find an approximation. So there are tricks up our sleeve, right? One thing we can do is we know that for the amplifier, is that non-ideal? Yeah, we know that actually this is the response of the transistor. So we just make sure that we go to this middle region, which is linear, and we only vary our input in this region, right? So then you can get an output. By the way, when you apply this DC voltage, VI, to the system, this is called biasing. And then when you're applying this input, this tiny input on top of VI, and you're looking at what the output should look like, that's your small signal analysis. You'll see DC analysis and small signal analysis in transistors. And that's what we mean by that. The DC analysis is how you get to point Q, and the small signal analysis is what happens to the output when I change the input around point Q, right? So we're kind of making our system linear. The same is true with a transistor, with diodes, right? The ideal is like this. The reality is more like this. But in our systems, if 0.7 volts is a very small voltage, relatively speaking, we ignore it. We can come up with different materials to reduce this voltage for our systems, the bias voltage. Or for the breakdown, it may actually be more of an opportunity. You can design a diode that works in this linear region rather than this linear region. And the good thing is this is like a test, right? If your voltage is smaller than -5 volts, your system turns on. Or you could switch it around and use it backwards. If your voltage is bigger than 5 volts, your system turns on. Smaller than 5 volts, it turns off. How nice. You just invented a button. right? So this is, you can actually take advantage of the other parts of the material, but most of the time we're dealing with things which are physical things, which are nonlinear, time-varying systems, and trying to make them fit our application. Okay, so it's physical structure of PN diode. Anything else that was fun here? There's a lot about op amps. I was going to show you this, which is the actual internals. It's slew rate over here. Yeah, and there are with op amps, with electronics and most of the stuff you'll be doing. I'll answer you in a minute, but most of the stuff you'll be doing, you know, you can learn it at a basic level, and then you can just go deeper and deeper into anything. So if you look at op amps at the very basic level, there's like 2 or 3 equations. Op amps are the most fun thing to analyze at this basic level because there's like 3 equations there. I is plus is 0, I minus is 0, V out is equal to V input, and you can just you just solve all these equations really quickly. But if you actually go into, oh, well, I minus is not exactly 0 and I plus is not exactly 0, and maybe we should model those. And maybe we should, you know, look at the output as well. This is supposed to be infinite, but infinite resistance at the output. I'm sorry, 0 resistance at the output, but maybe that's not exactly true. So you go into a deeper and more detailed model of the system, then you can do more analysis. If you need to, like if you need that kind of performance from the system, you're going to have to model it in more detail. Okay, I think that's enough electronics. I think everyone's had enough electronics. Do you guys have any questions? I'm going to get into grades in a minute, but you guys have any questions? Let me find that. I'll find the symbol for the Mosfet and stick it on there. So you guys should know this is a diode, this is JFET, this is BJT, this is Mosfet. I'll put the correct figures at the bottom. So download the notes later on. High pass filter removes the slowly varying signal and keeps the fast varying signal. A low pass filter removes the quickly varying signal and gets you the slowly varying signal, right? An amplifier just makes your signal and your noise bigger, right? By A. The voltage is multiplied by A, so the power is multiplied by A squared. And when you get to electronics classes, you will see this, don't panic, is the output input, V input versus V output graph, right? And you will use these to figure out what the output is given a certain input. And the same is true over here for a more realistic case. This is the actual V input versus V output. So basically, minus VI minus VO gives you this graph, more or less. Okay, any other questions, guys? Any questions? Okay, so let me answer these. When is the exam date? Let me just see. They sent out the exam dates. You know what? I can look it up now, but I can just put it up for you. Okay, let me write down here. Exam date. I'll put it in the. You know how I put the notes for the class? I'll put it up there. I'm just gonna write down exam date right here, so I don't forget. About the reading, I'm not reading the midterms, luckily, because I'm really sorry, guys. It's been very hard to do the grading. Like I'm not grading your papers, so I don't know, but I am grading other students' papers, and I'm in trouble with that. It's been very hard grading online. Just I don't know why. If I had a stack of papers in front of me, this would all be done a long time ago. But it's really hard to understand what you're saying. Sometimes the figures are messed up. Somebody sends JPEG, somebody else sends PDF. They all open on different apps, and we're all home all the time, which is also really aggravating. So yeah, all are, I mean, my grades are delayed. Grades for this class are delayed. We will get to it as quickly as we can. That's all I can tell you. I've been postponing my other class so I can finish the grading. But yeah, that's kind of the situation. Hopefully by next semester, we'll have some of the classes online. It would be really nice to have physical papers. In addition to the whole, it's nice to see students doing their work on the exam and not have bad suspicions about what's going on. In addition to that, I would really like to have physical papers as well. That was so much easier. It's great. Okay, so basically, I don't know when you're getting your marks, but I will look up the date for the final and put it online. Any other questions? What will be on the exam? Stuff from what we teach, mainly the examples. Today's stuff, I will tell you, what can I ask you? Like I said, I'm going to put up the proper symbols for the BJT, JFET, Mosfet diode drawn nicely. And I might just ask you, which one is this? Or something like that. What is a high-pass filter? What is a low-pass filter? If you understand what those are. What is an amplifier? So I didn't do anything with calculations today. Should I ask input output? Could you draw the output given the input? Do you think you guys could do that? I gave you like a simple figure and had you draw the output for it? Maybe. Yeah, I'll see about that. Maybe something like that. From the other one, I had a solved example. No, okay, fine. No, okay, fine. Never mind that. It's okay. I mean, I just wanted you guys to see what electronics is about. And the reason that I show you this is because I honestly did not understand this when I was doing biasing. And when I was taking electronics for the first time, I later took a class on op amps. And that's when I understood the biasing situation. Because with op amps, you see all those transistors, all of them have to be biased properly together. So the voltage VEE you apply isn't just VE, it's also VB for the other transistor, and you have to subtract and stuff. And there's a lot more calculation, but finally I got it. So the idea here, I wanted you to know what DC analysis and small signal analysis are, so that when you do them, you're not like, why am I doing two voltages here? Okay, they're both, one of them gets you to the point Q, the DC analysis, and the small signal analysis shows you how the signal input and output are varying around Q. When will it be? Because on the table we have today. So, okay, fine. I'll just look it up. It's in my Gmail. I don't want to open up my Gmail. Oh yeah, okay. I can open my Gmail over here, where you guys can't see. That's good. Let me see. I have literally papers opened up everywhere. Mail. Even check my email right now. Okay, there we go. Final class program. This was 10. Oh, I see. There's 2 dates, isn't there? Now I understand what you're asking because there's 2 dates for it. I'll talk to the other professors and let you know. I'm going to guess the first date just to get it over with, so we have less of a problem with grading. So the first date was on the 7th, 14th, is that right? Yeah, unless somebody has like unless one of the other professors has an issue with it, we'll probably do it on the 14th. Yeah. Where is this class? There we go. Introduction to Mechatronics, right? 14th, 12:30. Yeah, let's just do it on the 14th. I mean, they're both going to be on the same date. Either it's the 14th or the 21st. If you guys have a reason to want it on the 21st, like you have 3 exams on the same day or something, then we'll move it to the 21st. But I'm thinking the 14th just to finish and get it over with. Okay? Both 14th. Both 14th for both. For EE 104 and Mechatronics 104. Just have them both on the 14th. Because you're going to get the same exam. That's why. So I don't want to give the same. Otherwise, we have to come up with 2 sets of questions. And every time I do that, somebody gets more difficult questions and somebody gets easier questions. Not on purpose, But like any question, and sometimes not even like I think a certain question is more difficult, but students think the other one's more difficult. I see. That's why since you're taking the same class, you should take the same exam. So it'll both be on the 14th. Okay. 103, yes. Yes, basically. For me, I mean, I only taught after the midterm anyway, so for me, it doesn't matter. For Jihan Hoja and Nijat Hoja, I'll ask. But Nijat Hoja didn't even come for the, he didn't teach any classes after the midterm, did he? So yeah, I think the final is going to be comprehensive. You're responsible for everything on the final. Yeah, 14th. If it changes, I'll let you know, but at 14th. Any other questions? Okay. Thank you. Okay. Have a great break. And I'll see you guys after the break, I guess. No, I'm not going to see you in classes until your probably third year. So, okay. But hopefully we'll be on campus sooner or later and you can see me in the department. Okay. Any questions? Okay. Take care, guys. See you. Bye-bye.